finding values statistically. Basically, we're putting the process in reverse in regards to we first off were given values. We had to calculate a z-score, go to the z-table, find an area, and find a probability or a percent or an area from the z-table. Now we're given a percent. We have to look at our bell-shaped curve, take the percent, change it into an area, change that area, or change it into an area, and then go to our z-table and find the z-score. Once we find the z-score, we can back work and find what is our value of x at that point. You had 3 problems, 2 within, so you had 6 total problems. Questions you have about any of these problems? Once again, hopefully you're checking your solutions, you're working forward. Okay, opportunity, I try to pose the situation where you can have success out there if you push yourself and you do the work. Okay, obviously, if you just sort of slag along, you're going to struggle with the material a little bit more. So please keep up. Questions at all? Anything you need me to go through? All right, the last section. The last section in this chapter. It's called the central limit theorem. The central limit theorem. In essence, what we are doing with the central limit theorem is we'll just find or have a different way of calculating a z-value. What we are dealing with the central limit theorem. This is going to be a sampling distribution of sampling means. And what that means and what that is basically you have a distribution using the means computed from all possible random samples of specific size taken from a population. Go ahead and get it down there, and I'll try to simplify it a little bit in regards to what we are dealing with. It's a distribution using the means computed from all possible random samples of a specific size. In essence, what we're going to be doing here is, if we take a look, if we go back to our initial idea of a sample in a population, when we first started the class, I posed this opportunity or this situation where it's a way of being able to create the idea of sample and population. It is not impossible, but it's very difficult for one person or a couple people to go around the entire state of Ohio to measure the height of all 16 to 18-year-olds, to deal with the entire population. So what we talked about is looking at the idea of a sample. And in that sample, we said, well, maybe we just take 10 students from each high school. 10 students from each high school, and the phys ed teacher will take these 10 students from each high school and choose them at random and send them off, those 10 data points, send them off to a centralized person, and we got a sample then. And by the law of large numbers, we can create a very good estimate of the average height of males age 16 in the state of Ohio. Well, what the sampling distribution states is we still take every high school. We take every high school. We choose 15 males at random. And calculate the mean of those 15 males. And that mean, we send that mean as a data point. That is just one data point. This mean is now sent. And this is one data point where rather than sending 15 data points off to a centralized place or a centralized person, rather than sending those 15 out, we're just going to take the mean of those 15 and just send one data point. And each school is going to just send one data point. And what we will do with that one data point is we will calculate the mean of the means. We will calculate the mean of those means. We will calculate the standard deviation of the means. We will calculate the mean of the means and the standard deviation of the means. We will do a frequency diagram of the means. That is what a sampling distribution of the sampling means is. Rather than dealing with the 15 or 20 or 30 data points from each school, we're just going to deal with one data point from each school. And we'll calculate the mean of those means and the standard deviation of those means. Standard error. It's a difference between the sample measure and the corresponding population mean. It's your difference between the sample measure and the corresponding population mean due to the fact the sample is not a perfect representation of the population. We're going to have an error. And once again, for statisticians, people that do statistics, they're okay with errors. They're okay with being off a little bit. Because it's going to be close enough for them. They can still make predictions. They can still make guesstimates that are pretty accurate. You have guesstimates, you have estimates that are going to be pretty accurate based on these data values. And if you have a little bit of an error, so be it. That's the difference between statisticians and mathematicians. Mathematicians want exactness. If you're building a space shuttle, you need exactness. If you have a little bit of an error in the space shuttle, a bolt will come loose and something will blow up. That's mathematicians. That's scientists. You need exactness. Statisticians, it's okay to be off a little bit. It's okay. We're okay with that. Properties of a sample distribution. The mean of the sample means, okay, this is approximately equal to the population mean. The mean of the sample means is approximately equal to this population mean. And in the perfect world, they will be equal. In the perfect world. This is the realistic world right here. This is realistic. But in the perfect world, the mean of the sample means will be equal to the population mean. The standard deviation of the sample means will be smaller than the population standard deviation. The mean of the sample means will equal a population mean, but realistically it will be approximately equal to. The standard deviation of the sample means will be smaller than the population standard deviation. What this will do, the central limit theorem will do, is once again, it will just change somewhat, or change the way we calculate our z-value. Everything else is going to be the same. The formula for the z-value changes a little bit. The standard deviation of the sample means will be smaller than the population standard deviation. Okay. Now this is standard deviation. This is standard deviation for the sample means. We have a sigma with an x bar there. Okay, here we have sigma with just the x. This is the population standard deviation. This is standard deviation for the sample means. And what this is going to be equal to is this will equal to the population standard deviation divided by the square root of n. Where n is equal to your sample size. So when you talk about the population standard deviation, here's our population standard deviation. This is the standard deviation of the sample means. Okay, the standard deviation of the sample means will be smaller than the population standard deviation. How much is it smaller? Well, we take the square root of n, the sample size, we divide our standard deviation by that. This is the mean of the sample means. Mean of the sample means, you have a bar there. But as we talked about up here in property number 1, this is approximately equal to mu x, and we'll assume equal to mu x, which is a population mean. Once again, this is just going to change how we calculate our z-value. The central limit theorem. Sorry for so long. That's theorem. Central limit theorem. As the sample size increases, law of large numbers continues to come back. Law of large numbers. Without limit, the shape of the distribution of the sample means will taken with replacement from the population with a mean of mu and a standard deviation of mu x will approach a normal distribution. Sample size increases without limit. Law of large numbers. As your sample size increases, which is your law of large numbers, your mean and your standard deviation of the sample means, you will approximate or you will approach a normal distribution. Well, what's important about a normal distribution? Well, if we state it's a normal distribution, we can now go back to the z-tables. This allows us to get to z-tables. As we increase with size, without any bounds, we continue to increase. Your mean of the means and standard deviation of the means will approximate a normal distribution, and you'll approach a normal distribution. How we calculated our values to begin with, our z-value, was value minus mean divided by our standard deviation. Value minus mean divided by standard deviation. That's how we calculate our z-value to begin with. Now what we're talking about here is our value is now going to be our mean of the means. Okay, this is the sample means. This is our standard deviation of our sample means. So this gets replaced by sigma divided by square root of n. This is just changing how we calculate our z-value. Rather than value minus mean divided by standard deviation, we have the sample mean minus the population mean divided by the standard deviation for the sample means, which is your population standard deviation divided by n. We are just throwing in a division by the square root of n. We're using when we're gathering information about the sample means. When we're gathering information about the population, we still go back to value minus mean divided by standard deviation. What we've done in the past. Two key ideas to pick up from the central limit theorem. When the original variable is normally distributed, then the mean of the sample means will normally be distributed. And when the distribution of a variable might not be normal, the sample size of 30 is more is needed to get a normal distribution to approximate the sample means. The larger, the better. When the original variable is normally distributed, then the mean of the sample means will be normal. And when the distribution of a variable might not be normal, a sample size of 30 or more is needed to be used a normal distribution to approximate the sample means. The larger the sample, the better. Law of large numbers, once again, reflects into this. We will still be calculating a z-value. What you have to distinguish between, am I dealing with a single value from the population, or am I dealing with a set of sample means? If I'm dealing with a single value from the sample or from my population, I go back to what we've just did. When I'm talking about a set of sample means, my z-value is calculated by sigma divided by square root of n. Once again, the law of large numbers plays into consideration to everything that you do with respect to experimental data. A year and a half ago, when they were testing vaccines, or a year ago, they just didn't pick 10 people from the population and say, oh, well, let's give these 10 people this vaccine and see if it works. They did thousands upon thousands upon thousands of test cases with respect to the vaccines, because they need a large number of people. And that large number of people, basically, you can call them human guinea pigs. Because theoretically, they had it, yeah, this is how it's going to work on paper. We all know That's not always going to be true. FanDuel fans. I was supposed to get 40 points out of this person this week. They only got 2. I would have won. If they just would have scored what they were supposed to score, I would have won. Once again, as you go through this, you have to distinguish 2 different scenarios. One, am I pulling one person out of the population and testing that one person? Or am I testing a group of people out of the population and testing their sample means? All right, let's take a look at some problems. The mean weight of 15-year-old males is 142 pounds, and the standard deviation is 12.3 pounds. If a sample of 36 15-year-old males is selected, find the probability that the mean sample will be greater than 144.5 pounds. Assume normal distribution. Now, you're taking a sample of 36. And you want to predict the probability that their sample weight or their mean will be greater than 44.5 pounds. So what we're given here is a population mean of 142 pounds. We have a standard deviation of 12.3 pounds. And we're choosing a sample of 36 15-year-olds. And want to predict the probability that their weight is going to be greater than 144.5 pounds. What's the probability that their sample mean, that sample mean of 36 15-year-olds, is going to be greater than 144.5 pounds? So we're testing a sample mean now. We're not testing one individual and pulling one individual like we did the first 3 or 4 days with this. First 3 or 4 days, we were picking one person out and testing that one person. Now we're testing a sample size of 36. So we still go back to our z-value, but now our z is calculated by x bar minus mu divided by standard deviation divided by square root of n. Because we're dealing with a sample, we are testing a sample mean. We're not testing one individual. And we'll talk about that in a second, how we can adjust. So we have 144.5 minus 142 divided by my standard deviation, 12.3, divided by a square root of 36. Now, you have to watch your calculator. You can still quantify your top and your bottom and do one fell swoop of a z-value. Or if you want to just subtract the 2 on top, that is fine. Hit enter like you did before. But when you divide, you have to divide by the square root of the standard deviation divided by square root of n. So we have 144.5 minus the 142. If I hit enter, I get my 2.5. But now I have to divide by. You need to watch what you divide by. Quantity. What was my standard deviation? 12.3. Yeah. 12.3 divided by the square root. Well, it gives me a parenthesis there, so I need to close my parenthesis twice. Okay, I need to quantify that. I have to close this parenthesis with a radical and close the parenthesis in the bottom. And we should get 1.22. You can also quantify the top and bottom. Quantity 144.5 minus 142 divided by the quantity of the 12.3 divided by square root of 36. We get our 1.22. So now I go back to what I just did. I'm drawing a bell-shaped curve. At 1.22, 0, I want to find the probability that we are greater than the 144. So we're looking for this area right here. So I go to my table value, look up 1.22. That's going to give me this area right here. And then what do we have to do to find the area on the outside?
Subtract 0.5 or subtract 1.22 from 0.5.
Okay, not 1.22.
Or the z value.
Your z value, your table value. Okay, if we look up a table value for 1.22, you get 0.3888. That's our table value. And to find the outside, we're going to subtract from 0.5. What will it come down to, Ethan? So we have 11.12% chance that we have a mean weight of 140 or greater than 144.5 pounds. Once again, predicting probabilities. Now, you can go back to this and think mentally how you go through this, okay? Suppose I just had one person. If I'm calculating the mean for one person, what do? Well, I add up the 1 and divide by 1. So the mean of the one person is just whatever that measure is for the one person. If their average weight, if I said, I want to test the average weight of this one person I'm picking at random, what's the probability that their mean was 140 pounds? Well, the mean of 140 is 140. My sample size of one person is 1. So I'm dividing by the square root of 1, which basically takes this away. So this, in essence, will allow you to, if you remember this, it's a way of being able to transform this into if I just have one person. The average price of bacon, well, that's obviously changed right now because it costs about $7. You have a pig, man, you're in good if you have a pig right now. Okay? Average price of a pound of a sliced bacon is $2.02. Assume the standard deviation is 8 pennies. A random sample 41-pound packages is selected. Find the probability that the mean of the sample is less than 2 pounds or $2. So we have population mean at $2.02. We have a standard deviation of 0.08. I have a sample of 40. And I want to find what's the probability that this, if I have a sample 40, that the mean will be less than $2. So calculate your z-value. Calculate your z-value. Check that z-value with somebody around you. Do your bell-shaped curve. Go to your table. Hello. It's so fun being on this side of that. And once again, check all your answers on with somebody around you. What do we get for a z-value? Ethan, what do you get, sis?
0.4382.
0.4382 for z-value?
Oh, no. 1.54.
1.54? Can I say you a negative with that?
Yeah.
Negative 1.54, we good with that? Let's get some looks here. Anybody get that something different, or are we good with this?
I got negative 1.58.
Negative 1.58? Negative 1.58, negative 1.58. All right, redo your calculations, Ethan. Negative 1.58. So, taking this and go back to the idea of z is what we've done. What we're looking at basically is the probability that our z is less than negative 1.58. This takes us back to a question that we had at the very beginning. So we have negative 1.58. Okay, we get our table value. Jade, what's our table value? 0.4429. Then to calculate our area adjustment, what would we have to do? And what do you come up with?
0.0571.
So we have a 5.71% chance that if I took a sample of 40, that their mean would be less than $2. Once again, the more your sample increases, the closer you'll get to actual values. This is the last of the material from this chapter. Next couple days, we'll be reviewing ideas from the chapter. Probably look at a review day Monday and a quiz on Tuesday on this over this chapter. Solutions have been posted for you, and the rest of the time is yours.